Recording. Good afternoon again, everyone who is here and who is watching us offline as well. And this is our lecture 33 on high dimensional probability and applications in data science. We're finishing a big chapter today. The data that's around us is high dimensional. That's how we started this course. That's what we argued. But we are low dimensional creatures. Our mind cannot really hold more than 10 thoughts at a time or something like this. And so the big question is, what allows us as low dimensional, low complexity creatures to comprehend the world that is high dimensional, to visualize, to think about the data and the world, to lift this curse of high dimensionality. Our brain seems to do that pretty well. We don't see the world as a complete chaos around us. We can extract useful information. We can learn from the world. And this is not just a philosophical question. It's also a question about how do you implement that in a computer. If you are to build something like an artificial intelligence or just a modest goal of just learning from some data presented as a big matrix, like a million by million metrics, then that is a question. The matrix looks like a total chaos to you, but there must be something that allows you to learn from it. And here's a question. In the 20th century, the late 20th century, one of the reasonable explanations for this kind of paradox is was suggested as the following paradigm. So let's call it a low dimensional paradigm. That although the data can be high dimensional data, it has some low dimensional structure. I'll explain what exactly that means. Maybe think of this as a signal plus noise. The noise could be high dimensional, but hidden in there is some low dimensional structure that our minds and the computer is able to capture. So that is what will allow us to reduce the complexity in the world, that we're kind of filtering out the high dimensional noise around us and we're fixing on low dimensional data. As an example, for example, human decisions are based on 5 or 10 values, life values that we share, and that's social studies show that very well. Human faces, although they could be very complex, if you present them in a pixel picture, you can create millions of pixels of human face. We don't see our brains are not trained to see the pixels themselves. Our minds capture the faces based on maybe 5 or 10 features that we can recognize. I don't know, beard, no beard, brows, eyeglasses, stuff like that. How do we, in general, put this in a mathematical form? All this low dimensional paradigm. We can imagine the data as living in some low dimensional manifold. Let's say this is a very high dimensional space, RD. D is large. That's where the data lives. For example, human faces as presented in pictures. And we can imagine maybe actually there is a low dimensional manifold, low dimensional, a line or maybe a two-dimensional plane, curved plane or something like that, where the data actually lives, or maybe close to that. So the actual faces, the actual human decisions or something like this are near that. So this is let's see, this is a low dimensional manifold. Call it M, let's say. Suppose it's, I don't know, maybe R dimensional. And the data and the data actually live near that manifold. We do not know if that's true, actually. And the question is, the big question is, how do we find that manifold? Right? For example, for the human faces, is it possible? It's called manifold learning, but we're very far from understanding how do we find this manifold? How do we parameterize this manifold? If it really exists, think of human faces or genes, maybe. If it really exists, then let's say it's 5-dimensional, right? Then we can parameterize this manifold with 5 variables, and these 5 variables are the 5 features of the faces that we recognize. So maybe our brain does that. Maybe our brain does this parameterization of this manifold implicitly. It doesn't tell us about that, but maybe what we do is we parameterize this very complex pictures that are captured by our eyes. Our eyes do have pixels, by the way, right? So this, and maybe they reparameterize this, and it presents our brain with these 5 features that our brain can recognize. Maybe. We don't know. How do we know it isn't true? Can we even test that something like this is true? Maybe we don't find the manifold, but can we at least test that there is a manifold or not? Those are very, very big questions that no one really can answer in a satisfactory manner now. But in a very simple situation where we assume that maybe there is a linear manifold, then we can do that. So if we assume that manifold is linear space, is a linear subspace. So the situation looks like this. This is our M and this is our data. And the data lives near the linear manifold. Then we can do that. That's linear regression, basically, right? Or something like that. We want to fit the data to the linear manifold. So linear subspace of dimension R, that's less than D. Then we can test that. How do we test that? By the eigenvalues of the covariance matrix. So if X is a random vector that's uniformly distributed on the data, and this data points, the data lives in or close to, let's say, in the low dimension manifold M, then the covariance matrix sigma, let's say it's X is mean 0, so the covariance matrix is like this for simplicity, has very few non-zero eigenvalues, at least R. Non-zero eigenvalues. Why? Well, remember what that means. If this is our data here, the first eigenvector will be the longest direction of the data. That's V1, the first eigenvector of the covariance matrix, right? And the size of the data, the variance in that direction, that's the first eigenvalue. Right? So the first eigenvalue is the variance of the data in the longest direction. The second eigenvalue is the variance of the data in the orthogonal direction. And the third is the variance of the data in another orthogonal direction, and so on and so forth. So if the data lives only in R dimensions, then there are only R directions in which the data is non-flat. The others will be flat, and therefore the rest of the eigenvalues will automatically 0. Agreed? So that's a reason. It's just a geometric representation of the eigenvalues. So the situation of the eigenvalues lambda I will be like this. So there are eigenvalues 1, 2, 3, 4, 5, n, and there is R somewhere here. And the data looks like the eigenvalues looks like this. We arrange them in the non-increasing order, so they look like this. And then there's suddenly boom, and there's 0 at R. No, R is here. Yeah. So right there. So the eigenvalues suddenly drop, and that we can test, right? We can just take the covariance matrix, compute the covariance matrix of the data, and look at how the eigenvalues drop. If they drop exactly to 0, then the data is low dimensional. Perfect. And we can find the manifold by just eigenvectors. So that's pretty much understood. Now, of course, you look at this and you say, well, that never happens really, right? The eigenvalues never really do this, and then suddenly boom, and then drop to exactly 0. What happens in practice is that the eigenvalues do drop, but not to 0, right? So the more realistic picture of the data, the more realistic picture is something like this. Get values, they go to 0, they go to 0, then maybe there is a drop and they continue like this, and then they are 0. Even that is probably, Pavlo is smiling, so maybe even that is non-realistic, right? That there is some, no?
No, it's looks realistic.
Yeah, it could happen, right? It could happen that the eigenvalues kind of establish a smooth drop-off, let's say. 1, 2, and then at R they drop, and then there is, etc. There is n. And that, what does that mean then? If we see eigenvalues like this, then the data is not exactly R-dimensional, but what? Near R-dimensional, right? This is a picture. So the data don't exactly lie on the R-dimensional manifold, but near it. Maybe there is noise, and that's a realistic situation. That we can also test by the drop-off. So let's call, still a little bit non-rigorously, let's call this R the effective rank of sigma. Remember, the true rank of sigma, is this one, where the eigenvalues exactly drop to 0, the number of non-zero eigenvalues, that's a rank. And let's call, if you have an approximate drop-off, let's call it effective rank of sigma, which we may also call the effective dimension of the data. Effective dimension of the data. Okay, so that's hand wavy. How do we know whether it's a drop-off, right? What is a no drop-off? How do we define this mathematically? Let's try to do this mathematically now. To make a definition of the situation a little bit more mathematical. Here's, I don't know, there is no established definition, but here's what I just thought about this yesterday, and I thought, well, why don't we do this? Look at the data. Again, a little bit non-rigorously still, but if the eigenvalues seem to follow on this curve, like this, just find R right here that separates the area under this graph into 2 equal parts, 2 equal areas, this area and this area. So find the R, this one, that separates these parts into 2 equal areas. And call that R the effective dimension of the data. It kind of explains 50% of the variation in the data. So more, okay, this is still hand wavy because there is no area, it's a discrete situation. But the area is, well, it's a discrete situation, so the proxy for the area right here is just the sum of these eigenvalues, right? Just take the sum. So let's take that as a definition, the effective rank of any matrix, pretty much, of a positive semi-definite matrix sigma, which in our situation we also call the effective dimension of the data, is defined as the point that separates this eigenvalues into 2 equal halves. So it's the smallest point, smallest index, minimum R, so that the eigenvalues to the left are greater than the eigenvalues to the right. The smallest R with this property. So if I add even 1 to R, then the inequality will reverse. So that means that we're approximately dividing it into halves.
But don't we expect the left side to be heavier than the right side? because it's like the signal and
yeah, we want, yeah, exactly. We want that. Yes, exactly. So in what, yeah, I guess. So in what follows, in what we will prove now mathematically, you can replace that by any quantile. Okay, instead of dividing 50-50, you can divide 90-10, for example, and the results will be even better. So you can, and that's a great suggestion. So you can make a little parameter, which is a quantile, and introduce that into that definition. But just to make this simpler and to avoid that parameter, I just decided to use a median, so divide 50-50. But that's a good suggestion. Yes. Okay, so now what do we do? What did we achieve now? We suggested to look at the drop-off, exact drop-off. It was not possible. Maybe there's an approximate drop-off, but even if there's no approximate drop-off, we can always separate into two halves and make that the definition. And this is a rigorous definition now. Okay, that's a definition of the effective rank or the effective dimension of the data. All right, let's look at how it works in practice. Let's see. So here's an example of what's called Eigenfaces. It's a very cool data set that does consist of the images of human faces as presented to by a camera, by digital camera. So each image has maybe 10,000 pixels or so, maybe 50,000 pixels. Images of famous people. We represent each image as a vector. Let's say a binary vector. We just code the intensity, the colors of the pixels. So now it's a vector in a very, very high dimensional space, 50,000 dimensional space. And then we do we compute the covariance metrics and we compute the eigenvalues of it. So we do the PCA of the data. Here is the result. Yeah. So here is the result. First of all, I'll show you the eigenvectors. They're very cool. The eigenvectors of this data look like this. These are called eigenfaces. This is the top eigenface. It explains the most of the human face variability. That is this first eigenface and so on and so forth. Yes, I particularly like this one, eigenface, that explains how people smile. That's the eighth feature. And so on. And maybe that eigenface 11 explains that some people have mustache. And yeah, so the computer does that as eigenfaces, and the corresponding eigenvalues, I plotted them here. These are the eigenvalues. As you can see, the eigenvalues drop off dramatically, very quickly. The first eigenvalue is, I don't know, 5 to the 10 to the 8th. The next one is twice smaller and so on and so forth. There is a very, very good drop off. And let's compute the effective dimension of that. So I just approximately found the location that separates this graph into two equal areas, and it looks like it's 6. So 6 is the effective dimension of human faces, which means that this 6 facial features explain 50% of the variability of the human faces, which is pretty believable, I guess. Probably less, because we're operating on the assumption that everything is linear, like the faces actually are living in the linear manifold. So, but even that is very, very cool. Question from Konstantin: Is it some specific set of faces to get such results, or pretty much any set? There was a first experiment with the publicly available data set. I can't remember. It's called Human Faces in the Wild, HFW. It's a benchmark collection of human faces that's available to everyone, and that is the most famous one. But anyone can experiment with their own collection of human faces. All you need is just to normalize them in the same way, so without shifts, so you need to clip the faces, and you can make this experiments. And there are many examples of this database. But I think I took this one is the Human Faces in the Wild. It's a benchmark example of human faces of famous individuals. Yeah. Any other questions? Good. Okay. So what's the game now? Data is high dimensional, but maybe we say maybe there is low dimensional structure to it. And how do we make that? How do we use that? How do we leverage that fact in this low dimensional paradigm? The practical implication of this, effective dimension thing is that in all machine, okay, this is maybe a bold claim, all right, maybe I'm boasting a little bit, but in all machine learning results and algorithms, the linear algebraic dimension of the data, the formal dimension of the data, the number of pixels, for example, should be replaced by the effective dimension. Dimension R, which hopefully is much smaller. So the formal dimension doesn't really matter. And it's clear that for human faces, it doesn't matter, right? You buy a simple camera and you take a picture and it's 10,000 pixels. And you buy a more expensive camera, you take a picture, it's 1,000,000 pixels. But the human face is the same, right? The actual dimension of the human face is the same. It's just the formal dimension can be different. And so that's why we say that the actual dimension should not even matter. What matters is a true effective dimension. How do we find it is a different story. What we'll do now today is we will make one example of this claim. We will take the covariance estimation, or the PCA, exactly what the human faces, what we did with faces. We'll take the covariance estimation and we will there replace the formal dimension of the data by the effective dimension. We will say that to run PCA accurately, how much samples do we need? How much data do we need? We need the sample that's linear in size in R, in the effective dimension, not linear in size in D, the big dimension. So that's a much better result. The sample will be smaller. Okay, that's our goal for today.
So does it mean that for faces, for example, we will need like linear from 6? This is very little.
Yeah, we'll need maybe 10, 20 to get a good accuracy, but of that order. But to do what? Not to represent every particular detail of the face, but to get the faces recognizable, right? When we say we can do PCA or clustering with 90% accuracy, what does that mean? It doesn't mean that we do every single detail. It means that we can do, let's say, recognition of faces. We can tell one person from another with 90% accuracy. So just for that purpose, it's enough to have like 10, 20 features, facial features. Yes. That's how Eigenfaces came about in pattern recognition, in face recognition problems. Questions? Ask me questions, guys, if you. Okay, so our goal now. Sorry, where is this? Where are we? What are we doing? Okay, so our goal is to prove now that covariance estimation, sorry, and thus the PCA, principal component analysis, is accurate if the sample size is linear in the effective dimension. What we did previously, linear, actually there's some log factor, but that's okay. Let me put a star as a disclaimer that there is a log factor hidden here. What we did previously is that covariance estimation is accurate if n is linear in the in the formal dimension. So now we'll do this. This is better. It's because R is less than D. Good. Okay, let's do it. Theorem. I don't know who did it first. Maybe there's a long history to this. So Rudolphson established the first version of something that looked like this, and this one is due to myself in this form. So let X be a random vector in RD that represents the distribution of the data. We will assume that it doesn't have very, very bad outliers. So we will assume that its size is always, the data always live in a ball of radius, maybe 10 times expected radius. So there could be some outliers that go away from the expectation, but let's clip them. If you have them, just drop them. So let's assume that we clip these outliers, and the norm of X, or the length of X, is like that. So we clipped the data into 10 times the expected radius. Okay, here we go. Now it's the result. If n is greater than CR log D, so almost linear in the effective dimension, then the sample covariance approximates the true covariance very nicely. Just to recall the true covariance again, that's expected value of XX transpose. Sample covariance is you take n independent identically distributed copies of X. So you sample from the same distribution as X, and you form this expectation over the sample, in a sense. Good. Okay, so that's the result. Any questions? Yeah, look at this result one more time. If you let me know if there is anything that you want to clarify, anything that you want to get rid of, or something like that. I would like to get rid of this, but it's impossible. There's a counterexample. All these numbers are arbitrary. I could have put here epsilon instead of 0.1, but then this constant will depend on epsilon. And we could put any number here, k, but then the constant will depend on k. And they just wanted to get rid of all these parameters just to make it simple. Okay. Okay, good. So the main point here is that now we have the effective dimension here, R. That's what drives the size of the sample down. Okay. No questions? Then let's prove it. The proof is based on, again, on matrix-Bernstein's inequality. It's a nice exercise in applying matrix-Bernstein's inequality. First of all, let's compute this thing, and let's see how the effective dimension enters into this computation. That's the only place where the effective dimension will enter. So here will be a little lemma. We will claim that expected value of the norm squared is less than the effective dimension times the norm of sigma. Okay, that's a really nice exercise. Okay, let's do it. Left-hand side. The norm, we can write it as x. The norm squared is x transpose x. That's the inner product between x and x. And that gives us a norm squared. Agreed. Okay, now we do this little trick. We think of X transpose X as a 1-by-1 matrix. And we take its trace, which is, it does nothing. It's just the same thing. It's a tautology. But now we use the cyclic property of the trace that allows us trace AB equals trace BA. So it commutes. Trace X transpose. So I just swapped the order because of the cyclic property of the trace. Okay. At this point, X transpose is actually a matrix. Now it used to be a number, but now it's a true matrix. The expected value and the trace are both linear operations. So by linearity, we can swap their order. Trace expected value X transpose. I just use linearity of both trace and expected value to change their order. Good. And well, that's sigma. That is the sample covariance matrix. So we get this equal trace of sigma. Good. Okay. That's one part of the computation. The second part is to go to the spectral domain. The trace of sigma is the sum of all eigenvalues of sigma. Yeah, remember that? Good. This is the time where we will use the notion of effective rank. In the effective rank, the effective rank splits the sum into two almost equal sums, I less than R and I greater than R. I just split the sum into two parts. And what do we know about these parts? We know that the second part is smaller than the first one. That's how we define the effective rank. Let me go up the slide and show you how we define the effective rank right there. So we define the effective rank as the smallest number for which the left sum, the sum of the first eigenvalues, is greater than the right sum, the sum of the last eigenvalues. And that's why I put this sign here. Yeah, good. It's just by definition of R. And that is, well, if the second part is less than the first one, then the sum is less than twice times the first part. This is obvious, right? Second is less than that. Okay. And lambda I, we just bounded by the largest eigenvalue, lambda 1. And the largest eigenvalue is the operator norm of sigma. That's one of the definitions of the operator norm, the largest eigenvalue. That's it. So we get what? We have the sum of R terms. The sum has R terms. Each term is less than the norm of sigma. That's it. We're done. That's what we wanted to prove. Okay, any questions? Okay, cool. This is the only place where the effective rank will enter the picture. And now we prove the theorem in the same way as we did other results based on Matrix-Bernstein's inequality. So we'll use Matrix-Bernstein inequality from lecture 30 or 11. Why? How we can do this? Our goal is to bound the difference between the sample covariance matrix and the true covariance matrix. The sample covariance matrix is this. The true covariance matrix is sigma, but I can put sigma in each term like this. Yeah, that's because of the 1 over n times sum. Now what we have? We have the sum of what? Xi is a vector, so xi transpose is a matrix. This is a matrix. It's a random matrix. Xi is a random vector. This is a random matrix. And they're all what? They're all independent because xi's are independent. They are mean zero because I just subtracted their mean. Here. So this is the sum of independent and identically distributed mean zero random matrices. Exactly the situation in which matrix Bernstein's inequality is useful for. So now let's use matrix Bernstein's inequality. I will use the sign to hide absolute constant factors in front. So instead of writing something like this, I'll just drop C to simplify notation here. Matrix Bernstein's inequality bounds the sum like this. The first term, the main contribution, is sigma, which is basically the norm of the matrix variance. It's a sum of the variance xi transpose minus sigma squared. Just sum the variances of the terms. That, if I just finished here, that would be the ideal situation. That's ideal matrix Bernstein. It's not true, unfortunately. There are some nuisance factors, but that is the main term, sigma. Okay, so now the next terms. Matrix Bernstein hold with a log factor in front, and it also has this annoying factor k, which is the maximum norm of each term. I'll drop i's because they're all the same. And this holds with probability, with high probability, let's say 0.99. Okay. Remember or trust me, if you could look back in Bernstein's inequality, that's what we have. That the sum of IID random variables is less than, well, basically the variance. Actually, you know what? Yeah, that's right. Yeah, less than the standard deviation. Good. Okay, so now it's actually a boring part. Now the boring part is just to estimate sigma and k, just this and this. Let's do it. Well, maybe not boring, but it's a standard part. Sigma squared. First, we need to estimate the sigma squared. Let's do it. It's okay. So there is sum of n terms. All these terms are equal because they have identical distribution. All these xi's have identical distribution, so they're all the same. There's n of them. So I'll write it like this: expected value of xx transpose minus sigma. Agreed? Okay, perfect. Okay, what about each term? Let's represent each term. Squared, I forgot the square here. Okay, it's a positive matrix, non-negative matrix. Let's open the square. I don't know. Let's just open the square and see what happens. It's expected value of xx transpose squared minus expected value of the cross term transpose sigma minus expected value of the other cross term sigma xx transpose plus expected value of sigma squared. I just opened the square, nothing happened here, really. Okay, now let's see. Sigma is a deterministic metric, so that's going to be sigma squared. Expectation doesn't do anything to it, it's just a constant matrix. Well, because sigma is a deterministic matrix, we can pull it out of the expectation in both sides. Like this. the first term is expected value of, let's open the square again, x transpose, x transpose. And the second term is sigma times expected value of x transpose, which is sigma. That's how sigma is defined, so sigma squared. Similarly here, sigma, we pull it out, and expected value of x transpose is another sigma, sigma squared. Okay, this goes. This is the norm of x squared. X transpose x is just the inner product between x and x, which is a norm squared. And the norm squared, yeah, this is where we need some bound. The norm squared is bounded by, in our assumption, it's bounded by this. So that was why we assumed that thing. So it's bounded by 10 expected value of norm of x squared. And then we use the lemma. The expected value of the norm of x squared, we bounded by the effective rank. That's the only place how it enters. This is less than 20 r norm of sigma. This is by the lemma. Okay, we're almost there, almost done. So this is then, okay, so how do we use this? So this is less, as a matrix, it's less than, in the positive semi-definite order, it's 20r sigma, we put it out, times expected value of x transpose. That's the first term. Yeah, look it up, agree? X transpose x, we bounded by this term, and we pull it out that term, and what remains is x transpose. So put it there.
Which is sigma as well.
And minus sigma squared. Yes.
No, I was talking about the expectation of x transpose.
Mm-hmm.
Yeah, that's the next step.
Yeah, everything is all right, Pablo. Yeah, the sigma is there. Yeah, perfect. Minus sigma squared. And yeah, so we're good. This is, again, this is sigma. Oh, yeah, that's what you said. Yeah, this is sigma. And what we subtract is greater than 0 in the positive semi-definite order. So it's less than 20r norm of sigma times sigma. Hey, whatever, it's there. So what did we do? We bounded each term here, sandwiched each term here between 0 and this matrix. So what's its norm then? Its norm then is less than 20r sigma times norm sigma. So norm sigma squared. And so sigma squared, finally, this computation, sigma squared is bounded by n, 20rn times sigma squared. Woo, okay, that was quite a computation. Okay. We did half of the thing that we had to do, the harder half. We bounded sigma squared. And now we bound k, which we need to bound k, which is this. But that one is easy. K. The norm of sigma, the norm of x transpose minus sigma. Let's just do triangle inequality here. So bounded by xx, norm of xx transpose plus the norm of sigma. Okay, what's the norm of xx transpose? It's a rank 1 matrix. Yes, xx transpose. It's a rank 1 matrix, so it's got to have just one eigenvalue which determines its norm. And that eigenvalue is?
Norm of x.
The norm of x, exactly. Only it's squared. That's because x transposes. It's a norm of x squared, exactly. Which, again, is bounded by a 20R norm of sigma. So we get R is greater than 1, so it's 21R, let's say, norm sigma. That's our K. Ooh, okay. Done. Now we just substitute into this formula, into this matrix Bernstein's inequality, we just substitute, that should be norm here. Norm, I forgot the norms, everyone. So in the matrix Bernstein's inequality, we substitute sigma and K that we computed. And we get, okay, hold on with me, guys. Promise this is the last line here. So it's less than 1 over n. Then instead of this sigma, I replace it with the square root of that. So sigma squared is that. So 20, forget the 20, it gets absorbed by the constant. So root r n norm of sigma squared. And there is extra log d now. Log d plus, instead of k, we put the bound on it, which is r sigma, and another log k goes here. Log d goes here. Okay, I think we're good. So this is what the sigma is a common factor here for sure. The norm of sigma. Okay, and what's inside? This is the root r log d over n. And this is r log d over n. Oh, beautiful. Beautiful. So this is a general form of the matrix estimation. In fact, this is a more useful one. Let's sigma n minus sigma. This happens for any n and d. Oh, it's so cool. And in particular, this is less than 0.01 or 0.1, whatever we promised, 0.1 norm sigma, if we make n, this n, just beat the r log d. So greater than big absolute constant times r log d. And that proves the theorem. A little technical, but not too much, right? The main point is the main point is that you that we can look at the sample covariance matrix as a sum of independent random matrices, and that allows us to use matrix Bernstein inequality. So here is our theorem. Any questions about it?
So it might be something obvious, but so X is a random vector with effective rank R. So if it's a random vector, then like the concept of the effective rank that we discussed is for metrics.
The sample covariance the covariance matrix of R. Yes. So R,
the covariance matrix will have this effective rank.
Yeah, exactly. So we look at the
sigma, but it's also random.
No.
The sample covariance matrix.
Not the sample, the population covariance matrix. This one. This is sigma. The population covariance matrix is expected value of XX transpose. Because we take expectation, the matrix is non-random. Population covariance matrix is a constant matrix. It's not random, the deterministic one. And then for that matrix, we compute the effective rank. R equals R of sigma, the one that splits the eigenvalues into equal halves. So R is a non-random quantity. Yeah, is it good?
Yeah, thank you.
Yeah, you're welcome. Actually, but it leads to an interesting question. We don't know the effective rank of the population covariance matrix because we do not know the population covariance matrix. Isn't this a circular argument, right? We want to estimate the population covariance matrix, but the estimation is based on us knowing the effective rank of the same matrix that we do not know. How do we go about it? Actually, I don't know how. The obvious solution to this would be to estimate the effective rank of the covariance matrix by the effective rank of the sample covariance matrix of this one. And maybe they are the same. It's a good thing, good exercise to think about it. Are they the same or not? Or similar? Is estimation possible? Yeah. Couple more remarks here. You may first ask if the logarithm factor is needed, and Konstantin asked about that already, and many other people may be also interested. Is log oversampling needed here? The answer is yes, log sampling is needed. The result is false without log n, and that will be in the homework. So we'll actually construct an example for which log oversampling is needed. Another thing that's kind of hidden in this result, but it's a very strange thing that X is a random vector, but we do not place any distribution assumptions on X. It doesn't need to be Gaussian. It doesn't need to be sub-Gaussian with nice sub-Gaussian norm or something like this. It can be anything. And the result still holds. Which means in particular that X can be a very discrete distribution. The population distribution can be very, very discrete and has clusters and so very crazy, anything. So that's useful in general. The more recent work eliminates log, so it replaces D by R again. So CR log R. I think this is due to Stas Minsker from Southern California, 2017. Then the result becomes completely dimension-free. And the ongoing work in the area is to make this a robust thing. So, for example, if there are outliers, what do you do? If there's an adversarial outliers, what do you do? It's more related to security thing. So if there is an adversary comes and looks at your algorithm, adversary looks at your data, and then makes a very malicious decision. It just replaces some pieces of data by some other pieces of data, so that as to screw this algorithm to make it. How is it possible to protect yourself against these attacks? So this is a very, very interesting ongoing work of, for example, of Zhivatovsky hand up. And there are many other questions. It's really at the forefront of the modern research. So I'm glad we're talking about this. Hey guys, any other questions? It would be nice to, for example, to do this for kernel methods. The standing assumption is the data is near the linear manifold, but that's a little bit too much. The data is usually not near a linear subspace. What if it is near some nonlinear subspace? Can you do this? Well, kernel PCA coupled with, let's say, Gaussian kernel PCA, that's promising, but I don't think there are results available for that yet. So that's one direction that sounds promising to me, to generalize this to more realistic nonlinear situations. Good. All right, we finished a big chapter of our life together. And next thing we'll start mathematical theory of machine learning, supervised learning. Yes, congratulations, you achieved a lot already. It's a very big set of results that we proved, big intuition that we acquired. So that's great. So now we have just the last quarter, I think, quarter of the semester, maybe 1/3 of the semester to go. Good. Okay, if there is no questions, then maybe who can meet that we have not met with? Ilya, probably Ilya and TP. We did not meet with Ilya, right? I don't think.
Yeah, we didn't.
We didn't meet. Okay, let's meet with you. Is that possible?
Yes, sure.
Good. Okay, sounds good. And then have a wonderful weekend. Stay safe, and we'll see you on Monday.
Thank you so much.
Bye.
Thank you. Bye.
Bye.
Goodbye.
Thanks.
Bye.
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 I had one small, maybe it's just technical question about the two